complete basis sets and all that stuff. And so it's very nice and continuous for us to go through and solve for all the hydrogen atom, the radial wave function, and the angular wave function of the hydrogen atom. Okay? Then we went back and we did this formalism, and now we're going to use the formalism that we did in Chapter 3 to go and really investigate angular momentum and spin of the hydrogen atom. Okay? Okay. So we're going to look at angular momentum. So we are now back into Chapter 4. And what we're going to use is use the machinery of the matrix formalism to tackle angular momentum and in a particular case, which is intrinsic angular momentum, equals spin. All right, and spin is a how many dimensional space? Do you think so far? So look, here's the way I look at it. Do I know the functional form of spin?
Up or down?
All right, I don't. That up or down is not a functional form, right? Up or down is an abstraction, right? And how many spaces do I need in that abstract space? 2. And up and down, and one is zeros, and up and down is 0 and 1. So the whole thing about spin is you never come up with a functional form of what spin is that you continuously live in this abstract space, and it's way better to be there, right? So I never have because that's what it is, it's quantized, it's either up or it's down. I don't have a function, right? I have an abstract, complex space that's up or down. Okay. So the first step in this is to figure out angular momentum, and L equals R cross P. Everybody remember that?
Mm-hmm.
Yep. Okay, so let's do this. Let's build an angular momentum operator. How can I build an angular momentum operator?
Put the bracket around.
How about this? How about if I do R operator cross P operator?
Right.
All right. Do I know R operator and P operator?
Yeah.
R operator, so R is just a generalization. In 3 dimensions, X, Y, Z. In spherical, it's R hat, theta hat, phi hat. All right, but let's just do it in Cartesian coordinates to make our life easy. All right, so how about this? How about it equals, this is how I do it. I hat, J hat, K hat, and then X hat, Y hat, Z hat. And then minus IH partial with respect to X, minus IH partial with respect to Y, minus IH partial with respect to Z.
Do you want the hats on the X, Y, Z?
We'll go without it. Because, yeah, this is L equals. Yep, fine. Yep, good. All right. Have you guys ever seen how this is done? So I'm writing this cross product as a determinant. Have you guys seen how to make a cross product out of a determinant? Okay. And what this equals I hat times.
It's I hat.
This n.
Yeah, y
It will be
minus I h bar d by dz.
Y partial with respect to z.
Yeah.
Minus I h z partial with respect to y. So I get the idea. I'm going to be pulling out a lot of I h bars, but that's in the I hat direction, and then it's going to be plus. All right. Now across, no, so what I always have to do to get this right is here's X, Y, and Z. If I roll my fingers in the direction of X and turn into Y, I get Z. So I know that's the correct right-handed system. So this is I hat, this is J hat, this is K hat. All right? So the way I really do it is this. So let me erase this because I jumped. And I want to show you actually how I do this so that I don't get it wrong. So then when I draw this picture, I say, okay, how do I make my I hat component? Well, I got to go J cross k, right? Because if I go j cross k, my thumb points out and I get I hat. So then my I hat has to be j, so it has to be, because if you don't get this right, you're going to end up by a minus somewhere. All right? And so it may be that if you just go plus this, plus this, you end up with the same thing, like a true determinant. But I don't know. I do it more physically. Like I physically think, how can I make an I hat? The way I make an I hat is I cross a y into a z. So it's going to be this one. So let's take everything out of this in I h bar to get it out of the way. A y into the z is going to be minus y partial with respect to z minus z partial with respect to y. All right, and then I say, how do I want to form a j hat? Well, a j hat is k hat cross I hat, because that gives me y. Right? So I have to go k into I, so that means I got to go this one into this one. So this means plus minus z partial with respect to x minus, and then this one, which would be minus x partial with respect to z, and that's j hat. And then I have one more, and that's k hat. And so to make a k hat, I have to go x and y, and that will give me k hat. So it's going to be minus x partial with respect to y minus y partial with respect to x, and that's k hat. All right?
Did you just like way overcomplicate that, or I just totally lost?
I did it the way I did, which may be overcomplicating it for you. All right. So here's, whenever I take a cross product with a determinant, I know I'm going to end up with a vector. All right. And so my vector's got to be an I hat, j hat, and k hat, right? Because a cross product gives me a vector. And so what I do is I draw a little picture here, make sure I have it right-handed, and then I use my right hand to figure out the order of how to figure this all out. So, for example, I want my first component on my new vector is going to need an I hat. So how do I figure out an I hat? Well, to get it, if I have a right-handed system, I put my right hand in the direction of y and roll them into the z, right? And my thumb points outward, which is I hat. So that means I have to go y into z. So then I went y into z, and that's how I got my x control. Right? But I think it turns out to be exactly the same thing if you take a straight determinant, like we were just doing. Like go I hat times this stuff, then minus j hat, right? Does everybody see what I'm saying?
Yeah.
Everyone should know how to take a cross product by now.
Right. Yeah. But the question I have is, this is how I do it, but I think it comes out to be the straight determinant. Okay?
Cool.
Probably always switching in terms of the middle.
Yeah, they switch around, because there's going to be a minus. When you take the straight determinant, you're going to end up with a minus, so they switch two things. Go and do them both ways until you're happy and get it right, and you should get the right answer. Okay, so I'm not going to do this. It's kind of an exercise. It kind of is it's a little bit messy, but it's something you guys should all be able to do. And here's what we're going to do. We're next going to look at the commutation. Look at the commutation. Of Lx, Ly, and Lz. So let's call this Lx. This is Ly, and this is Lz. Alright, and this is equation 499 in the book, and what you get is Lx, Ly equals I h bar Lz, and then Ly Lz equals I h bar Lx, and then you have Lz Lx, and that equals I h bar Ly. Okay? So what does that mean? All right, and I'm going to throw in, so Dale was watching a lecture by Sidney Coleman, who is just an authority, period, on this stuff, and he's refined how we're going to interpret this. All right, but it's a slight redefinition, but it's important. Okay. All right. So how can we define this? So if these do not commute, what does it mean? So what does this mean, that Lx and Ly do not commute?
Oh, it means
Zero.
it means Lx, L comma X is not equal X comma L.
There's a deeper idea that we spend a long time talking about.
There is no L3.
What's that, Almar?
Last time we talked about like the uncertainty.
It's related to the uncertainty, yeah, and you get an uncertainty principle if it doesn't equal 0. All right. But here's what it is, guys, and this means you guys are not working hard enough, all right? No one came in having worked on that example problem. I mean, I had to reintroduce it, and nobody's up to date on this stuff. So you guys are not working hard enough, all right? I just got to tell you that, all right? We talked a lot about this. If the commutation does not equal 0, it means it doesn't share it doesn't share an eigenfunction that has simultaneous eigenvalues for both of those operators. All right, and I have to refine that from something Dale said. But the key thing is that what happens when two operators do commute?
It means it's a function of both.
It means that there's an eigenfunction that has
Both as variables.
It has the simultaneous eigenvalues of both. All right? So that will never change. That definition doesn't get redefined. What Dale came up with from Sidney Coleman is that when they don't commute, it doesn't mean that there isn't a function that has that doesn't have. It just means there's at least one function where they can't be measured simultaneously. All right? So that's just that's his refinement of it. But it doesn't change the essence of what we're doing.
And this one, I don't think it matters because it's complete.
Right. It doesn't change the essence of what we're doing, because even if there's one function out there, we don't want to deal with those. You know, so what we really want to deal with is when they do commute, because when they do commute, it means that there's an eigenfunction that works for both of them. And so I'd like to emphasize that aspect of it more, but I want to correct what I had said earlier. All right? So for now, what it means is that there's no simultaneous eigenfunction of these things, or there might be, but there's at least some functions that don't, so we're going to stay away from this.